Good morning, good afternoon, and good evening, everyone. My name is Marloes Slot from the Womanium Foundation and from the National Institute of Standards and Technology and Georgetown University in the US. It is my pleasure to chair this wonderful session about quantum games and simulations. We will start off with Shaeema Zaman with a beautiful talk about quantum games and simulations, applications in quantum physics, education, outreach, and research. Shaeema is a physicist and science communicator with research experience spanning quantum physics education and outreach using games and simulations, astrophysics, and quantum control. She completed her PhD at Aarhus University in Denmark and then started her startup, Science Melting Pot, driven by her passion for science outreach. She was also one of the nominees for the Danish Women in Physics 2021 prize for her dedication to physics teaching and outreach by the KIF network. Shaeema, very curious for your talk. Please take it away.
Thank you so much. Thank you so much for the introduction and also having me as an invited speaker for the talk. I think it's really wonderful. In general, for QWorld, I think it's a fantastic network. Yes, so I'll dive in right away. I'm going to present my little bit of my PhD research that I did in the last 3 years, and it was about exploring the use of quantum games and simulations and trying to look at how games and simulations can be powerful in quantum physics education, outreach, and research. And just a little bit about me. I'm originally from India, and then I first did my master's in physics in India. Then I worked as a science communicator again in India. And after 5 years, I moved to Denmark. I was just looking for more opportunities. And then I did my PhD in Aarhus University in Denmark in quantum games. And after my PhD, which I finished last year, I took a break for about 6 months, and then I decided to start my own company called Science Melting Pot. And it's about education, outreach, and the overall sort of vision or goal that I want to achieve is to sort of make science inclusive and accessible by having different services and products. Great, and this is a little bit of the introduction to the talk. One might wonder why games and simulations. We've already seen in various fields, games have been, or simulations have been very powerful in visualizing complex phenomena and has been used for education, for teaching and learning. For outreach, it's been used for playful tools or even to build curiosity. And for research, which is more in the serious games aspect, is how games can be powerful in crowdsourcing solutions to research problems. So these have been seen across a variety of fields like biotechnology, in physics, quantum physics, and then I'm going to dive into a few projects that I worked on during my PhD. So just an outline, so I'll cover these 4 projects and very briefly sort of spend 10 minutes each, about 5 to 10 minutes each on these projects. One is a simulation tool, one is an outreach training program that I helped co-mentor. Then one is Quantum Moves 2, a game, a citizen science game that I designed with my research team, and another game called Lab Manager. I couldn't manage to complete my research on this game, but I just wanted to introduce the game if someone is curious and would like to use it in the future. Okay. So I'll start with simulation tools, and then I'm going to present it one project at a time. So this is the first project. When you think about simulation tools, we have currently simulation tools like the PhET project, the physics educational project. And these are like applets. So if you just log into the browser, it's browser-based, you see the simulation, and it's very intuitive. You can click checkboxes and select some things from the menu. And so, they've done a lot of research about how it has been beneficial in student learning. But one sort of drawback is that you cannot make your own simulation. The functionalities are hard-coded. And if you want to make your own simulation, one would often need some programming language already that someone would have that knowledge. So there's this, on one end, we have applets, and then on the other hand, we have these text-based programming tools. Both have their advantages and disadvantages, but my PhD, I tried to explore what is the middle ground where we can combine an intuitive interface and yet have open-ended exploration where one can build their own simulations and sort of combine the best from both sides of the spectrum of simulations. And one tool I worked on is called Quantum Composer. This is a tool during my PhD I co-developed with my research group, and it's a visual-based programming tool. You can still make your own simulations, but it's visual-based, so you need not necessarily need to know any programming language. So, for example, this is the interface, how it looks like. You have a node tray on the left. You can drag and drop things into a flow scene, and then you can connect them. So you can actually see what input is going and then what output is coming out. So you can see in this Hamiltonian, you enter the potential, and then this is an example where I'm just simulating, visualizing a harmonic oscillator. What's interesting is one can define their own potential. So you can go from a harmonic or single harmonic oscillator to a double harmonic oscillator. You can make even more complicated or experimentally relevant potentials as well. For example, maybe an optical lattice where you have you would have multiple harmonic oscillators or multiple wells together. And this is so it's a very visual based. You can still enter, play around with different numbers and see what visualization you get based on user defined inputs. And very briefly, it can be, so it still has its limitations in terms of you can still have open-ended exploration, but it's restricted to one-dimensional quantum systems, but you can do both time-independent and dependent. And the tool currently functionality has a Schrodinger equation, so you can simulate single particle physics and also Bose-Einstein condensates. This is an overview. So I developed this tool, and we also used it, made some exercises that's available on the website and can be integrated in the classroom and we have it at all levels, from undergraduate, from actually advanced high school to research level. And then this research study. So we made the tool and we wanted to know how does it help student learning and engagement. So our sort of overarching question was how did students use Composer and their impact on learning quantum mechanics. So we first introduced, and we did this research with a group of students from the bachelor's course in nanoscience course. So they were not physics, like core physics, but it was a nanoscience course, and so which they had a quantum mechanics course within their nanoscience course. So we gave them, first did some exercises, and then from this we wanted, we recruited some participants. So we got 5 volunteers who wanted to test it out with us. We did some think aloud interviews with them. Those think aloud interviews is a very interesting way of interviewing and getting to know how people interact with the tool. So while they're working with the tool, in this case Composer, they would talk loudly about what they're thinking. So they would say, okay, now I have to connect this input with that output. Okay, this doesn't make sense, or this is a little difficult. So we recorded their voices and the screen, what they were doing on the screen, which would later be analyzed. So an example of an exercise could be, okay, this is what is the real part of the wave function of an energy eigenstate look like, or a superposition state look like, and finding. So you once you click on it, you would have these visualization. They could create their own superposition and visualize it on the plots. And to analyze them, we structured the exercise in such a way that they first had to solve a question without using Composer. Then they explored it using Composer, and then we tried to see if there was any revising their understanding after using Composer. And this research study we did after they finished their quantum mechanics course. So they already had all the theory that was done in their classrooms, and then we did this research study. So when they answered questions without using Composer, we relied on what they learned in their classroom. And this activity was analyzed using a code book. So we listened to the interview we looked at 1 minute of each interview, divided the whole interview into 1 minute chunks and looked at exactly what they did in that 1 minute and tried to find correlations. And yeah. And then sort of the key findings here, because one, or sort of a more broad overview, is we've tried to find if they could find correct answers and reasoning to quantum mechanics questions. We wanted to see how many were correct before using Composer and how many were after. We actually saw that even if students had gone through all the theory in their classroom, there were still quite a few correct answers that were missing. And after using Composer, we saw like a jump. And the questions were finding out how does the real part of an energy eigenstate evolve over time, or imaginary part of a. So really basic questions about energy eigenstates or superposition states as well. So this slide is to basically show that before using Composer and after using Composer, we actually found a big difference in almost the number of correct answers becoming double. In terms of reasoning, and this plot on the right where you have a pie chart, reasoning was really very hard to figure out, because a lot of people, even if they would give correct answers, a lot of times they gave a correct answer, but they didn't give a correct reasoning, or a reasoning was incomplete. So reasoning is something that we really have to dive deep into. And I feel, I mean, the study I did could not really capture that reasoning part so much. But during the interview, these were some things that they said, that for the real part, I mean, especially I like to say the quotes where this student says, it was nice seeing a visualization in Composer, because sometimes when I'm just looking at the equations, it doesn't give you the interpretation of the wave functions. And that's exactly what we wanted to do with this tool, to give the more physical and dynamic aspect of the equations, because one might know how to solve the Schrodinger equation completely, and but still might not know what is the physical interpretation of it, or even have a visual model of it. So, I mean, as a summary, we saw that after using Composer, students provided correct answers. We recommend that this tool should be used with accompanying textbooks. I mean, as a standalone tool, it might still not be very useful, because you still need some theory to understand the reasoning, and then you see the visualization from the tool. And one really powerful thing we think about the tool is that often curriculum textbooks will have a harmonic oscillator. We have a finite well or infinite well. Like if you just open Griffiths, you would have these very classic examples. And then using this tool, we can encourage students to think sort of beyond these classic examples that can be shown in the book, or even like very difficult, intractable to solve analytically. And this is the second project. So that was the simulation. And we also wanted to, after building this tool, we wanted to use the simulation to, so that PhD students can use them to do some outreach as well. And overall also do some outreach, train physicists to be good communicators. And the context is that I was part of this network called Cusco, and they had a work package called Outreach. And that's because there is currently a demand for researchers to engage in outreach, but actually researchers typically do not get any formal outreach training. People learn on themselves or are very motivated, and some actually also don't want to do any outreach, and there are different reasons. And so there is a need, but then there's a gap. So we tried to do this outreach training program with this group of physicists, 15 network PhD students, 15 PhD students in the network. And one of our focus was actually how do you use simulations in games as a dissemination tool to talk about quantum mechanics. It was a pretty long program. In a lot of PhD programs have just one outreach workshop, maybe because they will have an outreach workshop in a conference, which is like a 2 to 3 hour. But we tried to have a very long one, which was a series of different training workshops. It could be a workshop or a talk or an event. So in total, we had all these sessions, 11 sessions, and which ran over almost 2 years. So we would do a session once every month or once every 2 months. And the ultimate goal was to sort of create a portfolio of whatever outreach training they went through. They also created something out of it, and then to create like a portfolio of things. We had a very we had a lot of emphasis on also brainstorming, giving also expert feedback. A lot of training programs have a lot of peer feedback, so they divide people into groups, but we also wanted to give some expert feedback. And I think that later in the research, when the students found that quite valuable as well. These are just some examples, like they wrote a blog, simulation. So it also created this library of different outreach products, and which they could share it, have it on their group website, also share it on social media, and so on. These are some just brief examples. This is a blog where someone wrote how to microwave a diamond. This blog was about research on NV centers. We really found some really nice creative ways where students express their research by using infographics and blogs and videos. This is an outreach portfolio. This is an outreach. We created an outreach portfolio so that students later, after a PhD, if they wanted to get into a science communication career, they could use this portfolio as something that they could apply for a job application. This we found very valuable, so this, because students thought, okay, it's something that's actually going to help in the career if they get into a science communication career. But even otherwise, like science communication can always be beneficial, even like giving a conference presentation or teaching to bachelor students. Yes, like I think this one novelty was that we had this range of outreach products that they created. It was also a long timeline, like almost like a PhD timeline, that they did these outreach products, and then an outreach portfolio was created. And so far we haven't seen any outreach portfolio in the sort of quantum physics PhD network. So this is like one of the few sort of new things we did in outreach training for quantum physicists. Then we also had, at the end, we had a survey. We wanted to know what did they learn and enjoy, and did they think it was something beneficial. We used surveys, students filled the surveys and also their supervisors, and it was a mix of different kinds of multiple choice and also open-ended questions. And these are some things we found that the PhD students enjoyed the workshop series. Initially, it was a little hard to get people engaged because there is a systemic problem of not giving enough importance to science communication. So at the end, when students said that they really enjoyed it and they would recommend this to other PhD students, it was really great to get this feedback. Students specifically said that they initially thought science communication would be easy. You just have to talk about your research. But then when they actually have to do it, they really felt proud when they were successful in simplifying complex concepts. These were again some results. A lot of people agreed that they will use their portfolio for interviews. And that was one of the prime objectives of creating like an outreach portfolio, which they would show that they use games, simulations, or a blog to do outreach. There was one interesting thing, like, but we also asked supervisors to fill the survey, and we actually found that a lot of supervisors didn't want their PhD students to go through any training. Like 38% disagreed that it should be mandatory, or yeah. So we find this, and the students also said that even if they wanted to do outreach, they wouldn't get support from the supervisors. So there is a sort of, we need interventions also with the supervisors so that they can support the PhD students to be engaged in outreach training, and sort of have changed the mindset of outreach and communication training being something beneficial for the students. And this is, now I dive into the game I created. It's a citizen science game. We're going to hear more about sort of the different kind of definition of quantum games from Laura's talk. And this falls into the category of serious games, where we crowdsource solutions for a quantum physics problem. So what was the problem? The problem we simulated was quantum control. And very briefly, quantum control is when you want to control any quantum mechanical system to create desired behavior, for example, creating entangled states or even superposition states. And these are sort of the basic requirement when we're creating quantum technology. So it's really at the base level. Once you achieve quantum control, you can build on that to do other things. If someone's new to quantum control, I just thought, okay, maybe it's brief. So what's the mathematical description? you have a control function. This is all sort of the theory that builds around. And I looked at something called controls for a state transfer problem. So you move an atom from state A to state B, and that state A and B have to have a perfect overlap when we move it. So not disturbing the atom at all, and trying to achieve a particular target state. And then this becomes the optimization problem. Like, how close can we get to target state? We start with an initial state of an atom, manipulate it, and we want it to be as close as a target state that we want it to be. And this is measured by fidelity. And then we find out the overlap between the fidelity and the final state, which is called fidelity. And fidelity goal is to get as close to 1. So fidelity would be from, depending on experiment to experiment, it would range from 0.99 to 0.999 or something. And this is essentially like an optimization problem. We try with a trial solution, which is called the seed. We try a solution, and then we try to find better solutions and then optimize it. So yeah, I'm not diving into really the mathematics of it because I just want to give, but please feel free to ask me questions later if you want any specific clarification of the math behind. And I think if you want to take away what quantum control is, very briefly, if you think about you have you're a pirate, you have a target ship in front of you, and you want to shoot down the target ship. So you're thinking how much wind is there, what are your constraints, what's the distance, and you try something out. You try a guess, which means like you make a guess angle at which you want to shoot the cannon to the target. Then you try it out. Then actually see, oh, it actually didn't quite hit the target ship, but it was there somewhere close. So then you come up with a better estimate, and the loop continues. So it's a lot of optimization. We start with a trial solution, and then we optimize and to find what is the best possible solution. But sometimes it's really hard to know, if you find a solution, could there be a better solution? It's like, if you're blindfolded and you're going up a mountain peak, and you feel you've reached the peak, but actually once you reach there, you're like, okay, there is another mountain peak. So it's like to say, you found one solution, but if you try another technique or try another optimization algorithm, you might find even better solutions. But then you do so much computational stuff that you ultimately end up needing a cluster of computers to find out what is the best optimal solution. And that's what usually is done by using a purely computational approach. Put in a set of instructions. You have these algorithms like grape, or machine learning is now coming up as well. And you put in all these instructions and find out what is the optimal solution. In my PhD, I tried to approach this with a citizen science approach, which is that we took the problem, gamified it. It was a computer game where people could play the game. And whenever they played the game, they provided us solutions. These solutions were then analyzed to see how these solutions could be, are these good solutions? If they were good, how did players find them? Was there any pattern, and so on? And then we also wanted to see if we combine the computational approach and the citizen science approach, does it give an edge over a purely computational approach? So, and this has been done before in protein folding, for example, in biotechnology, where finding protein folding is also finding the best ways proteins can fold was also an optimization problem. So we sort of got inspired from those kind of problems and said, okay, we can also apply it to maybe quantum mechanics problems. And this is what we simulated in the game. So if you think about this is an array of atoms here, and then we would shine this is like in a real experiment, if you want to trap atoms, you would focus powerful lasers to trap atoms, which is an optical tweezer. When you zoom into one, you find the atom is trapped in this sort of well-like. And then this was simulated basically in a game where we showed this visualization, an atom being trapped by powerful lasers. And this is how the game looks like, where the challenge is to pick up the atom, which is like, this is the wave function. So we have this sort of wavy liquid going back, and we have to match the red and the yellow line. Sort of, this is the overlap between initial state and the target state. And then you get the fidelity, one can optimize, and then so on. So there was a tutorial in the game. So before people dived into playing the game, we gave them like a tutorial of a step-by-step instructions of how to play. Otherwise, it does need a little bit of instruction in the beginning to go through the whole game. And this was what was happening. This is what's happening behind the game. We simulated these levels were inspired from some real experiments in Vienna by Jörg Schmidtmeyer's group. He works a lot with atoms trapped in optical tweezers, BECs. So we tried sort of getting inspired from there and looking at all those experiments, trying to get, okay, what is being done in the lab, and simplifying that and creating some simulation and trying to understand what's going on in the math. So this was all the mathematics behind the game. What potentials we use, how do we control the atom, and how is the atom going to evolve in time? We applied a time-dependent Schrödinger equation to see how the atom evolved. So all of this actually took about 1.5 to 2 years to really dive in and do the simulation. And we collaborated with some game designers as well. So it was quite an interdisciplinary project. And yeah, it was fun. I mean, I learned a lot also from the whole process, and it was really interesting. So these were the main 3 scientific problems. We also had a single particle. We also had like moving Bose-Einstein condensate. So these Bose-Einstein condensate physics were also being simulated in 2 levels. And at the end, we actually found that solutions where solutions from the players were actually quite good. I mean, even if they had no knowledge about quantum physics, but because it was in a gamified format and they did a lot of trial and error, we found that they did give some solutions that were good. One thing was players did not optimize so much as we thought. So we still used those solutions and we optimized it further. So when we combined players' initial solutions and then optimized them, that seemed to be really promising, and sometimes even better than a computational algorithm. Then we also tried to see what strategies are players using, and we interestingly found some strategies that they were using, that it was actually quantum tunneling, but they didn't know it was quantum tunneling. But then that's what the visualization motivated them to use these tricks. But and at the back end, if you actually look at it, the quantum tunneling was one of the strategies they used. So these were some to analyze. We had 1,500 players. We had this competition called Regame. I'll talk about that a little bit. And then we had 1,500 players playing the game. These were the solutions, what we call player seeds. So all of this was just in the game, and back end, we were collecting all of this data and working on it and optimizing it. And we also used a computer cluster. And so there was like a full-fledged data crunching and trying to analyze these solutions. Yes. And now we also use the game for education, because to get data, we also did these school workshops. We went to different schools. We also taught them what the game is about, some quantum mechanics, and we had this framework called research enabling game-based education. The idea is that students play a game, but the gameplay contributes to a real-world research problem. So that's research enabling. And we're using gameplay to nurture this process of scientific inquiry. Using games, they can find out, okay, why is this happening? And sort of answering questions. So where they have fun and organically also learn and ask questions. This is sort of an example. So we would give them a task like this, move the potential up and down and see when can you get a high score. And then when they would get a high score, we would tell them, okay, this works because in quantum mechanics, you have this concept called quantum tunneling. And then when you have a double well, so it was, you still need an instructor to explain all of this and sort of drive to students, but we had these exercise sheets and the people playing the game as well. This is also a master's student that I supervised. We also did some research, and we found that I learned something about quantum physics in the learning track. And then here we got a mean value of 4.7. So we're not entirely, it still needs some more work, but it was a starting point to understand if it was something that they learned about something about quantum physics in this whole learning track. And this, I'm going to now dive into, this is my last project. It's called Lab Manager. This was a simulation game on managing a research laboratory. I think in academia, we are always managing. If you're an experimentalist, you have a lab where you have to think about, okay, what equipment you have, what research you want to do, how many PhDs or postdocs you want to have in your research group. And so we created a game about managing a lab. So, and sometimes you need to make trade-offs in laboratory management. And it's not something that in academia we're taught, we just learn on the go. So we designed this game to understand what is the best optimal way to manage a laboratory. Here it was a cold atom laboratory. So you could hire students, you could, every time you could buy some equipment. So you had a fixed amount of money. So how would you optimize and to get good science, but also have enough money left to continue the research. So, and so on. Unfortunately, like I couldn't do research on this game. I mean, it was something that we really spent a lot of time making, and it could have had more potential. But yeah, it's just, my PhD was for 3 years and we really had to like cut short, yeah. But that's the next steps. I don't know in my research group if anyone is taking this forward, but at that time we really thought that, you know, it's whatever players investigate. Again, if this game is given to people to play, and when they play this game, can they give us some strategies on how best to manage a lab? It's again crowdsourcing solutions. And we also wanted to investigate how much physics they learn from the game. For example, they start with laser cooling, trapping, and then what kind of experiments they could do. So there would be like a flow chart, like if we're here, if you see. So you can have different kinds of, it's a sort of step-by-step build up to doing different kind of experiments. And so like a technology tree. Yes, so this is just sort of more future a vision that I had at that time, and it would be cool to do it. So just to sort of coming to an end, I'd like to conclude that quantum games and simulations are indeed quite powerful tools that can help in science outreach, can help as crowdsourcing solutions, in this case, quantum control research, and also in physics education. So, and it's really, I think it's also very beneficial to have like this one common interface that ties research, education, and outreach together. So yes, I would like to conclude by that. Just a brief thing about my team. I mean, a lot of the stuff I did was with a group of a lot of talented people. And so I would also like to thank my team here. And yes, that's about it. Thank you so much.
Thank you very much, Shaeema, for this amazing talk. I think the audience is really enthusiastic, as was visible in the chat, lively conversations. This is really amazing work, and I think it will be useful for everyone to learn more and in the teaching. So I'm happy to see that it is available online, for example, the Quantum Composer. I invite you to read the chat later on, because there are many compliments.
Yeah.
Also some questions. Let me scroll up. First, about a quantum composer, there was a suggestion, extend it for 3D. It would be extremely useful. And maybe a broader question, are there plans to expand it? Maybe also blogosphere related or other useful tools?
Yes, I also feel 3D would really expand, and also to have more interesting physics like spin physics. So, you know, thinking of so right now it's more position-based physics, I would say, like, you know, how it's evolving in space and time. Spin physics would be so interesting to also visualize. And right now, I think there are plans, but there's been a manpower issue, workforce issue, sorry, yeah, workforce. And as far, and I'm no longer in the group right now. So, but at that time, I remember that it was because to develop a tool, we also wanted someone who could do the back end and also could do the front end interface. So you need to have like two skill sets that came in, and we had two people doing it. We had a front end person who made this interface look visual and intuitive. Yeah.
Okay, and if it's about manpower, there are 115 people here. So if someone feels addressed, then I'm sure they can send an email to you. Let me continue. Oxana asks, what is the computation power behind Composer? How complex systems can it simulate? I imagine there is a classical computer behind it, right? Is it an HPC?
Yes, it's a classical computer, yeah. And a computational, so right now it can, it's all based on time independent Schrodinger equation, time dependent Schrodinger equation. For the BEC, for the Bose-Einstein condensate physics, we have this Gross-Pitowski equation. So right now it has these only like these two formalisms that it can calculate. It is quite heavy in the sense that it's computer based, like we were thinking to also have it maybe on a tablet, maybe something that can be browser based, because it's a tool now that one has to download and understand, but it's really hard to make it browser based because the math library that has to be there, it just takes so long that it doesn't work well on a browser based.
Yeah, very good point. Then a question from Laura about the training program for outreach. She has noticed most PhD students are not interested in outreach at all. Did you also approach the motivation behind this? And did you help them to understand why it is useful for them? I think later on you addressed it a little bit, also addressing the supervisor's role, right? Could you comment on it further?
Yes, I think this was something, it's a really good question because we want to do this outreach. We had the money for it. We had, the students initially were not interested. They thought it was a distraction from their regular research. And also they already had a lot of stuff to do. Okay, they have to do research, writing papers. Some universities, some PhD students also had to teach, to be teaching assistants. So, and I think what clicked, we told them that this is something that you could benefit in your career. And sometimes people think career means just having maybe a programming skill, but just having basic communication skill really takes someone a long way. Even if you're going to a conference, I think it's just always nice to start with something that's basic and introductory, because in a conference you will have people from all fields. Even in quantum physics, there would be people from someone doing maybe ion traps, someone doing optical lattices. And just to start out with something that everyone can understand, you need communication science outreach skills there. You need science outreach skills with teaching graduate students or high school students. And then so we had to frame it like that. This is going to benefit you in your career. And at the end, you will create this range of outreach products and which you can use it. Like if someone wants to know, oh, what are you doing? What is your research about? Instead of sending them a publication, you can send them also your blog. And then you can say, okay, this is basically what my research is. This is someone who's outside your field. It could also be a journalist maybe, or it could be just a friend or, you know, your family also. And it helps in networking. But it was a challenge. I must say, in the first two sessions, we didn't find the PhD students very motivated. It was a concern about how do we actually get them motivated. And again, and on this part, one big challenge is they do not get support from the supervisors. So even if PhD students want to do it, some of the supervisors will say, okay, this is not important right now, focus on this. And then they don't do it. So there's a systemic issue as well, a culture, yeah.
Yeah, very recognizable and great points. I totally agree. Thank you so much. Laura asks, are these exercises related to Quantum Moves 2 available somewhere?
I think, let me just pull this up. Maybe something like this one?
Yes.
These exercises? Yeah, it's actually available in my thesis. There is, I don't think there's no online version now. So that's another thing, drawback about these things. Sometimes we do these projects, but they are not evolving because you just have a fixed 3-year PhD program that ends, and then this material just stays somewhere. Right now it's in my thesis. So I can, in my thesis, if you go like in the appendix, then one can find it there.
Great, that is.
And I can send it around if anyone else is also interested, yeah.
Perfect. Then there were some suggestions. Spin Drops project has nice spin visualizations when you were talking about a quantum composer.
Yeah, Spin Drops is really good. I would recommend. It's a tool made by Munich, TUM, Technical University Munich. Yeah, it's very cool.
Great, and thank you for that comment, Laura. Oxana mentions joining the QT Edu community would be the best place to collaborate on these cool developments. And she also posted earlier that the quantum composer is available there. Great. Yes, please read through all the enthusiastic comments. And then I would like to thank you again, Shaeema, for this amazing talk and for inspiring everyone.
Thank you so much. Thank you. And I'll just go through the chat now. It looks really interesting. Yes. And I will stop sharing and